I'm Joshua Bardwell, and you're going to learn something today. This is the next video in my Blackbox 101 series, where I teach you to tune and troubleshoot your quadcopter using Blackbox. This video is a part of a series. If you haven't watched the earlier ones in the series, you're definitely going to want to start at the beginning and go from there. The videos build on each other, and if you haven't watched the earlier ones, you might end up more confused than you started. Those of you who are watching the whole playlist have heard me say that many times. There's a link to the playlist in the video description. You can go check it out down there. In this video, we are going to be talking about the third of the PID terms, the D term. We've talked about P, we've talked about I, and we've talked about D. And in the other videos on P and I gave you kind of an intellectual, an academic description of what the term did. And I'm not going to do that for the D term. And the reason I'm not going to do that is it's a little hard to explain really accurately what the D term does without getting into calculus. The D term is a derivative, and we often think of the D term as damping. And in a practical sense, what the D term does is it damps P term oscillations. And you can go ahead and you can check out my video series, my PID tuning masterclass, where again, you can search my channel, or there's a playlist I put down in the video description. In that video series, I took the D term, I took the P gain up to a high value, and then I showed the effect of raising the D gain a little bit at a time. And that's actually what we're going to be looking at here in this video. We're going to be looking at the black box logs. If you want to see the practical, like what you would see in your goggles when you do the things that I'm going to show you here, you can go watch the PID tuning masterclass series. They really actually complement each other very well. And I think the way to understand the D term is to think about its practical effects and not worry too much about sort of on a mathematical, conceptual level what it's doing underneath. It's a little hard to explain accurately, and it's a little hard to understand, I think, for a lot of people. So that's what we're going to do here. We're not going to go deep into academia. We're just going to just study the practical effects of the D term. So if we take a look at this log, I'm going to show you the header, and I'm going to show you that the D gain here is 30. Now this is a little higher than the defaults are in Betaflight, but it's not too far off from defaults. And in fact, on many of the copters that I tune, I set the D gain to 30 or 35 just right off the bat, because I know that I'm probably going to end up raising it. If I typically end up with D gain around 45 or 50, perhaps, just throwing out these numbers, then I really can feel reasonably safe raising it to 30. I know I'm going to raise it some more. Sometimes people ask me, when you tune, do you want to start from like 0? Or do you want to start from defaults, or where do you want to start from? And I don't think there's much point in starting from 0. Some people set I and D to 0 and tune P. And my point is that if you know you're going to end up with an I of at least, say, 20 and a D of at least, say, 20, then start tuning with them there, and you'll save yourself a little bit of time. Anyway, our D gains are 30 here, and that's on both pitch and roll. This is not a perfectly symmetrical copter, so we would not, in fact, expect to end up with a tune with the D gains equivalent. We would typically expect that if the copter is more spread out on the pitch axis, we would have a higher P and D gain on, and probably I gain too, on the pitch axis. But for the sake of this example, that doesn't really matter. We're just looking at the behavior. We're not trying to find a perfect tune here. Our P gain is 7 or 70 in Betaflight. Again, the black box viewer shows the old style PIDs where they look like 7.0. In Betaflight, they would be 70. And that's high enough that when the D gain was 0, it was causing really bad P term oscillations. We'll take a look at that. What I want you to take from this, though, is that the scenario we're seeing is a mildly elevated P term and then a mildly elevated D term to sort of cancel it out. And again, if you want to hear more about the relationship between P and D and their practical effects, check out my PID tuning masterclass playlist. So essentially, this is going to be normal-ish behavior for P and D. And that's why I picked it as the first example to show you. I've got here gyro, P, and D on the graph. And I'm showing you P and D because P and D always interrelate. There's always a relationship between them. D is not necessarily based directly on P. D is often based on error. D is a function of error. Sometimes, though, D is not a function of error, but of measurement or the gyro, how exactly. And in Betaflight 329 somewhere, where we got the set point weight slider, it's not based on either one of those things absolutely, but on some amalgam of them. So again, this is a case where what's going on under the hood is actually pretty complicated and a little hard to explain. And we're just going to kind of gloss over it and say there's a relationship between P and D, and let's take a look at what that relationship is. So I'm going to scroll forward, and what I can see, P is the blue line, D is the yellow line. And what I want to show you is that D and P have a very similar shape quite a lot of the time, almost as if D is mirroring P. And if we look, we can see that D is slightly leading P. So you can see chronologically the earlier thing is to the left and the later thing is to the right. And so you can see here that D goes up and P is trailing it. Okay? And that is oftentimes what you're going to see. That is what you should see. That's what D does by its very nature, being a derivative. And here we can start to see how D has the practical effect of damping p-term oscillations, because we can see that as P is falling, D has started falling first. I'm going to change this zoom setting and zoom in a little bit on these to make them a little bigger. We haven't talked about the zoom setting much, but pretty self-evident. I'm going to change that. Yeah, I'm going to make that a little bigger so you can see it a little better. Wouldn't it be nice if we could zoom with control? No, it doesn't work. So what we can see here is that when the P term turns around and begins to fall, the D term begins to fall sooner. So here we're approaching the point where the P will turn around, and the D is actually already going down and becoming negative. And this is how D and P work together to affect the PID sum. The PID sum literally being the mathematical sum of these three terms, the P, the I, and the D. We can see that as P is climbing, D begins to climb as well and will be adding to the PID sum, in other words, accentuating the effect. And then as P turns around and begins descending, D does the same thing and has sort of a dampening effect on the PID sum. And that is essentially what you're always going to see. Now what we see here is a reasonably well-behaved D term. It's more or less the same shape as the P term. We don't see a lot of crazy spikes or oscillations. But if we go through here, for example, we can see that there are times when the D term gets sort of out of control, and the D term, the thing is that the D term amplifies. A D term, a derivative, in the same way that an integral is essentially a low-pass filter, a derivative is essentially a high-pass filter. And what that means is that it lets through all the crazy spikes, and it kind of doesn't let through. It isn't affected by the lower magnitude stuff. And essentially, what that means is that it amplifies noise. So as noise is happening in the system, the D term will amplify that, and that will come out the PID sum. And so we can see here, for example, we've got a spike in the P term. Now these are being scaled to the same magnitude. We've got a spike here in the P term, but the spike in the D term is much bigger. And we've got this activity here in the P term, but the activity is amplified in the D term. And as things start to get worse, you can see that the D term starts to get really messy here in a way that the P term really isn't. And it gets really crazy. And then settles down again. So one of the things we look at when we evaluate the D term is we want to look for cases where the D term kind of starts to get really crazy and out of control. And if that's happening too much, we're going to get hot motors. And hot motors, now that's not something you can see in Blackbox, at least until our motors get temperature telemetry, and maybe someday that'll happen. That is a thing that exists, is a brushless motor with a temperature sensor in it. We don't use them though. As long as the motors are cool, the D term it's kind of okay. I like to say as long as the motors are cool and the copter's flying how you want it, then don't worry too much. Now in this case, the P gain, I remember that for this copter, I felt like the optimal P gain was around 50. And so the P gain here is higher than I thought was optimal. And so we're going to get more P term oscillation and correspondingly more D term activity. But here we go back to relatively normal flight. This was probably like a prop wash turn. Let's watch the sticks. We jam the throttle. I guess I jammed the throttle here, and that made this oscillations come out. Good, normal. Now see here again, we got this big spike in the D term. That's something that, if it was happening a lot, would indicate that we had problems. I will say though, this copter is flying fine. It's not flying the best. I mean, I think it flew a little better with a P gain of 50 and a D gain. I don't remember what the final D gain was, but it's flying fine. So what I'm showing you is not in any terms a bad example. Even though this looks really bad, doesn't it? I mean, look at all that. No, this is not bad. And part of the challenge with D term is that assessing the D term in black box it's not always obvious when there was a time when I could look at a black box and go, yeah, that D term looks too noisy. But the filtering in Betaflight and other things that Betaflight has done have really expanded the tuning envelope to the point where it's something like this, which looks like just a complete mess. See the P term oscillations here, right? There's those sinusoidal oscillations, and the D term is kind of flipping out, trying to deal with those. That's actually not really a problem. Oh yeah, look at that. Oh, that's good. Let's see. Gyro oscillation, P term oscillations, and here's the D term. Let me I'd have to take the zoom back down slightly to get it. So if we zoom out slightly so we can see the P and the D together, and it's not going off the top of the graph, we can see here's some P term oscillations. And again, notice that the D term is leading. It's going first. And so that's how it is trying to sort of cancel out and damp down those oscillations. One of the things I like to do is, let's do this. Let's remove all graphs. We're going to add a custom graph of the gyro on roll. And I'm going to add a custom graph of the D term on roll. And what I'm going to do is I'm going to press the Z key on the keyboard, or the Z key for those of you in areas that say that. And that will zoom all the way out. And I'm going to press the S key to turn off any smoothing that's happening in the viewer, not a lot. And I want to look for cases where the D term kind of flips out. And I want to see that there's not too much noise in the D term. And by definition, what you're looking at here is not too much noise, because the copter was flying fine, the motors were cool. We can certainly see that there are periods where it's calm and periods where it's kind of flipping out, right? The gyro itself is not excessively noisy though. This is the filtered gyro data though. Notice that here I've dropped the throttle and I'm doing a roll. The D term is really working hard here. Again, as long as the motors are cool and you like the way the copter's flying, the D term is fine. And here is the most extreme example that I was brave enough to come up with. In this case, the D gain is 90 and the P gain is 70. This is very excessive D gain. This is not a good way to fly. And you can see that the D term is very messy. It's never really settles down. It's always kind of flipping out here. And sometimes it's worse and sometimes it's better, but it's always just really freaking out. Right? This is definitely excessive D gain. Although I will point out that my motors were cool. I could hear some D term oscillation. And in fact, if you want to, we can look at what the D term oscillation looks like. That'll be kind of cool. Let's add the motors in here. Oh my God, look at these motor traces. Can you believe this? Let me zoom back in again. So if we look at these motor traces, we can just see the D term is constantly oscillating and the motors are constantly oscillating. Do you remember I told you that D term oscillations, oh, that was in the PID tuning masterclass, sorry, and other videos. I've said that D term oscillation can be distinguished from P term oscillation because D term oscillation has overtones, or kind of a crickety sound. When I talk about those overtones, what I'm referring to is these oscillations that you see. It looks like an audio waveform. Well, it is an audio waveform. When the motors start attempting to make this shape, you know, by speeding up and slowing down, they make sound. It's probably not a direct reflection of the audio waveform, but it's probably not too far off. And here We can see motors maxing out and dropping as this oscillation happens. This is really, and in fact, wow, we can see the D term having almost a sinusoidal oscillation shape. That is something really rare. You almost, that looks like P term oscillations, but it's not. That means the D term is approaching the limit of the physical system's ability to sort of oscillate. And you can just see these motors going back. These are the back two motors. You can just see them trading off which one is maxed out. And also you can see a lot of oscillation here in the front motors as well. Wow, that's actually really cool how they trade off. The back left is maxed, and then the back left dips, and the back right is maxed, and they just keep trading off. And that's that oscillation that I told you and showed you in the, oh sorry, if you haven't watched it, the PID tuning masterclass video. Yeah, crazy. So this is excessive D gain, but I don't suggest you fly like this. But interestingly, the motors were reasonably cool, and the copter didn't fly terrible. And so I show you these things so you can look. I mean, if somebody hands you a black box and says, hey, what do you think of this? If you look at the D term, and if you look at the motors and they look like this, and you look at the D term and it looks like this, it's excessive D gain. It's way excessive. It's terrible, right? This is just a mess. Let's go back and to the earlier one, and let's just remind ourselves what that should look like. Oh, see, this is not too bad. This is a little messy. Again, we got our motors here, our D gain here, our D term here. It's a little messy, but it's not the end of the world. And this was perfectly flyable. What was the gain here? 30. Yeah. See, this is an example of not too messy, not too bad. That other example was super extreme, but surprisingly flyable. And so I think it's really challenging to tune D gain just by looking at the black box logs, because something that looks really sloppy may be flying exactly how you want it. And this is an interesting exercise and can help us sort of find really extreme cases. But even there was a time when I would have looked at this and said, this is terrible. You're going to burn up your motors. And for whatever reason, probably the filtering that's in Betaflight, that just doesn't happen today. You can fly like this and it's not really a risk. D-term interacts strongly with the filters. So it's critical as you're raising D gains that your filters are operating correctly. And we can look at the spectral, let's do this. If we look at the gyros, right, we can look at the frequency, the spectrum for the gyro. And what we really should be doing is looking, this is the filtered gyro data, okay? And so this is what's after the filters. And you see how clean this is? There's like no noise anywhere, right? And that's one reason why we can afford to raise the D gain so high without burning up our motors, because again, I said the D term amplifies noise, but in this case, there just isn't any noise getting through the filters. I have a video on how to tune your notch filter that shows you how to look at the pre-filtered data and adjust your filters to tweak them if you feel like that's something you want to do. But I don't think that's necessary or desirable for the majority of pilots. Some of you out there really want to tune everything to the nth degree, in which case you certainly can try and tweak your filters, but the default filters work really well for the majority of setups. And the default filters have relatively low delay. The advantage of tweaking your filters would be that you would decrease the delay. But the default filters don't have a ton of delay, and they cover the majority of situations. So you probably don't need to tweak them, and you can just set your D gain where you feel like it needs to be. If you're getting hot motors on relatively low D gain, then it may make sense to come in here and try to see if your filters maybe aren't quite matching up with your spectrum. And you can take a look at the video I have on how to set up your notch filter if you want to do that. That's not strictly speaking part of this playlist, but it certainly does fit in here. Well, there you go. There is your look at the D term. Now we've looked at the P, the I, and the D, and we're going to go from here in future videos into what I want to do in future videos is look at specific troubleshooting scenarios, look at what specific types of problems look like in Blackbox, and also discuss some general usability stuff. Like I haven't shown you the shortcuts and other things. If you take a look, obviously, if you take a look at the menu, you can see these things for yourself, but make a video or at least show them to you. Thanks for watching. Hope this was educational. Leave any questions you've got down in the comments, of course, and as always, happy flying.